In this video, we're going to be discussing about ellipses and the special attributes that it has. To the left of the screen, you can see a graph of an ellipse based on the function parentheses x minus h squared over a squared plus y minus k squared over b squared is equal to 1. The function you see on the right hand side is its function, its general function of an ellipse with its major axis parallel to the x-axis. Furthermore, we can see of points D and E, which correspond to the ellipse's focal points, which I'll be discussing later in this video. And we see its center as hk, which are the same h and k values as these two right here within the parentheses. So how do you determine that? Well, based on this definition of a general ellipse function right here, we know that its center point will be the value that x is subtracting by and the value y is subtracting by, correspondingly to a way how you would label a coordinate point in a coordinate grid. So, the center point of this ellipse in the general function will be hk, where h is the value that x is subtracting by and k is the value y is subtracting by. Then we have points D and E, which I've labeled here as its focal points. One of the very interesting things that conic sections have in their graphs is that each of the each of the equations or graphs as such have focal points, where if I do an example here onto the graph, if I have a beam of light that shoots out from anywhere, it does not have to start from here, but shoots out from anywhere and hits one of the sides of the ellipse, it'll bounce off and go through one of the focal points. That is essentially what a focal point is. It's like a focus center and the locus of all points where it's most concentrated. So essentially, this is the points D and E are the points where it's the most concentrated points along the ellipse. And notice how the focal points always occur on the major axis of an ellipse. They do not occur on the minor axis of an ellipse, which is segment B, as here drawn in this red color. B segment, or in red, is the minor axis, and this section drawn in this yellow color is the major axis, which is the value of A, the minor axis, the value of B, correspondingly to the same A within this general function, the A and the B. They are the distances of the major and minor axes respectively. Then returning back to our topic of focal points, which are in this case points D and E. So how do we find the focal points? Well, we cannot find the focal points without knowing their focal distances, which by definition is the distance between the focus point to the conic section's center, which in this case is hk. So the focal distance of this, let's do focal distance as an f. The focal distance represented in f will be equal to the square root of a squared minus b squared. And it's key to note that in this circumstance, a is greater than b. And only is because a is greater than b that we have an ellipse that is drawn like this with the major axes corresponding or parallel to the x-axis. If b is greater than a, the ellipse will not look like this, but it will look like an ellipse with the major axis parallel to the y-axis and the minor axis parallel to the x-axis. So that will look very narrow left and right and very stretched out up and down. But back to the subject of focal distances. Now that we have our focal distance, we can find the focal points, which points D and E will be respectively h plus minus square root of a squared minus b squared k, where h plus square root of a squared minus b squared k is point E, and point D is h minus square root of a squared minus b squared k, as we can know because if we add square root of a squared minus b squared, we'll be going in the right direction, which will reach the point E right here. And if we go left, we have to subtract the focal distance from the center value, which will go back to point D. And now that we have the focal points under our belt, along with the center and the general function for an ellipse with its major axis parallel to the x-axis, there's one more thing that we need to note before we move on, and that is from this distance right here, which is known as D1, Add to any other D2 which does not have to go through the focal points, D2. The sum of their two distances will be equal to 2a, or 2 times the major axis length, which is a in this case. So with that, let us move on to the second elliptical function, which is when the ellipse is like this. And the ellipse looks kind of like a mirror. Well, this general function for this kind of ellipse will be y minus k squared over b squared plus x minus h squared over a squared is equal to 1. Or in this case, b is greater than a. Furthermore, just like the ellipse with its major axis parallel to the x-axis, we know that this ellipse also has focal distances and focal points, which if I draw the axes like so, its focal distance will be along its major axis or somewhere about here. And it's to note, this is an estimation. They are along the major axis, but I'm supposing that the focal points are there. And there are points A and D. Well, what are their coordinates? Likewise, you must find the focal distance in order to find out, which in this case, once again, before we begin, the center is HK. And the focal distance is the major axis squared, which in this case is b squared, subtracted by the minor axis squared, which in this case is a squared. So now we have their focal distances from the point HK, or also their center. So therefore, we can rewrite points A and D, respectively, as HK plus minus square root of b squared minus a squared. Which if HK plus square root of b squared minus a squared will give us point A, and point D, we'll have HK minus square root of b squared minus a squared. Likewise with the reasoning that we did for the other previous ellipse, which is if we subtract, we'll be going down, if we add, we'll be going up to the respective focal points. So now we have the center and the focal points and the focal distance of this ellipse under our belts. Let us move on to another attribute of these ellipses, which are, once again, any distance added up. So we have D1 right here, and note it has to touch one of the points on the ellipse first, then going down here, which is unknown, I'll call it D2. Their sums, which I can be writing right here, their sums will be equal to 2b, 2 times their major axis length. And furthermore, just like how we have focal distances, we also have directrixes, which we'll be explaining in further detail in the next video. But just as in general outline as a wrap up for this video, a ellipse with the major axis to be parallel to the y-axis will have a directrix to look like something like this. It's a straight line, by the way. And with this function, we'll have a directrix that something looks like this. And I ran out of room on the left, but it will be outwards, not within the ellipse. Where in the next video we'll be also discussing its eccentricity and its directrix formulas. But in this video, I hope you have understood the concepts of an ellipse and the general function of ellipse as such, and we'll be applying examples and worksheets that will be found in the description below. Thank you for watching.